I'm here today to help raise the safety and the reliability of your substations in general. And I want to take a real quick minute to steal something from the fitness industry, right? A lot of us are into fitness these days. And here's my basic motto: that any activity is better than inactivity, right? We know this when it comes to our fitness, that sitting on the couch is not as good as getting up and just going for a walk. And so once again, I'm going to bring in some simple ideas just like that to help you improve the safety and the reliability of your substations. Really quick into the agenda. Hey, we're going to hit really quick what types of substations. The last time we did one of these, some people wanted to talk about some different equipment. So I've thrown in some new information there. Routine inspections. What are you doing in and day out? Maintenance testing. I got some new technology that we're also going to weave into some basic information about maintenance testing, right? What do we need to do to maintain our substations, and how can companies like ours help you guys out? So hopefully, and once again, I also want to point out, if you do have questions, put them in the chat so that Randy and I can knock them down later. So really quickly, I mean, substations come in a couple of different varieties. Some of you guys have substations that got a great big chain link fence around it, lots of outdoor bus work, switches in the air, breakers on the ground, things of that nature. Some of you guys, you might call this a substation, right? And on some level, they're made up of a lot of the same basic components, right? Over here, we have a transformer. Over here, we have a switch. Next to it, we have a liquid filled transformer. Inside this box is that same bus work, those same pieces, those same insulators are all inside of there. And once again, then we've got our breakers here. As you can see, very similar situation. We've got the bus work, we've got the breakers, we got our liquid filled transformer. So regardless of which type of substation you have, regardless of whether it's a 161,000 volt delivery at your facility, or you're taking it at 13,800 volts, there's going to be some great stuff in here, and it easily applies back and forth between medium voltage and high voltage, and I'll hit some of that. And I also want to encourage you guys to stay around later today. We're going to have iGuard talking about a new product they have for making sure that your 480 volt equipment can be worked on in an electrically safe condition. So I definitely want to point that out for you folks to stay around and hear the iGuard presentation. So let's get started. Quality is not an act, it is a habit. This is from Aristotle. This is about whatever the daily, weekly, monthly tasks that you guys are doing to ensure the safety and the reliability of your substation. I mean, little things like in this, like say in the background picture here, this image, are your filters in good condition? Are we keeping the bugs and the dirt and the grime as much as possible out of our gear? And are our heaters working? I mean, back here in this area right here, let me get my pointer up. This is a heater right over here. If these heaters aren't working, you could create moisture inside your gear, and moisture inside electrical equipment, as a general rule, is a bad idea. So once again, we want to focus on making sure that things like that are working properly. So let's dive right in. We had a client that was not maintaining their transformer nitrogen system. And that, of course, led to, and it was particularly this load tap changer right here. If I get my point in the right place, low tap changer, right? They ran their nitrogen bottle down to 0, and that allowed moisture to kind of work its way into the transformer tank. Now, the reason I bring that up, because moisture, once again, is bad inside of our transformer equipment, but in particular, what was the cost, right? What was the cost? The simple method of just checking the gauge. Like I say that, now I've got a picture of that gauge right here. Once again, the simple process of just checking that gauge, make sure I've got nitrogen both in my tank and in my system, keeps that moisture from getting into the load tap changer. But when that moisture got in there, it had to, of course, get repaired. And of course, we're talking about days of downtime, probably tens of thousands of, maybe even as much as $90,000 to $100,000 to basically take this unit offline, take it apart, dewater it, repair it, put the oil back in it, retest everything, and put it back online. So once again, a significant amount of money is incurred for something as simple as just not maintaining a nitrogen system, right? I did want to point out this particular nitrogen system that I chose to share a picture with you guys today is actually sitting at almost 6 PSI. I don't know how clearly that comes across in the presentation, but it's sitting at 6 PSI. That's way too much. Once again, for anybody that's on the call, familiar with liquid filled transformers, that's right around the pressure level that we might start raising our pressure relief devices. So once again, too little is not good. Too much is not good either. So once again, we want to make sure that we're doing a qualified walk around. Do we have the particular eye to what it is that we are looking to guard off or to protect ourselves from when we do these walk arounds? And this was one that I say that we found recently. Here's another item I want to point out is that low de-energized tap changers should be locked out. And you guys can see this right here. It's got the A, B, C, D around it. That's not locked. And somebody could easily, once again, somebody that's not qualified could easily come up and go, hey, what's this handle do? Move it to a new position and destroy your transformer. So once again, we want to just little things like that. When we're doing our walk arounds, those are some of the things that I'm particularly focused on. Once again, put a lock on there, automatically improve the reliability of your substation, because now nobody can monkey with your load tap changer. Here's something that's really simple for me. I'm not sure exactly why this happens, but when we walk around or start up a new substation, are we looking at our temperature gauges? Are we making sure our fans are working? And I'll cover why fans are important on our transformers here in just a second. But I just want to point out whether you've got the, let's see, get my pointer again, whether you're got a gauge type or an electronic type of fan package. Once again, this is a fan package, or a gauge coming out of a substation outdoor transformer. This is an example of any of my friends online here that have an indoor transformer, right? You probably are familiar with one or both of these types of temperature packages or temperature gauges. And interesting to point out that these temperatures, this little orange dot right here, is the first step in the fans, right? So as the temperature comes up, this white needle will get to this little switch that hides in behind the gauge, and it's going to start the fans. Well, you'll note that that's set at, what is that, 40, 60, probably 70, what is that, 60, 65 degrees C. And that's not a high temperature, but as I'll point out on the next slide here, it is going to shorten the life of our transformer. The cooler we can run our transformers, the longer they're going to last. And I'll just use this as a quick example. If we have a 1% dry transformer operating at 70 degrees C, that transformer's life expectancy, based on the paper that I note below, is going to last about 100 years. Well, just a simple increase of 20 degrees C, once again, same 1% dryness on our transformer, operating at 90 degrees C, shortens that lifespan down to almost 10 years. So a significant decrease just with a 20 degrees C temperature rise. So I always like to encourage our clients to, hey, let's lower these down to, something that's reasonable. I mean, 40, 50, 60 degrees C, something in there. I oftentimes see the dry type transformers set at as much as 110. Once again, that's the same, that is the rating of the insulation, right? But once again, if we can run our transformers cooler, by and large, they're going to last longer. And we've already hit that slide. Another one, this is like, the minimum barrier to entry if you want to have good substation maintenance and good substation practices, and that is get your thermographic surveys done. Once again, we had a thermographic problem show up on this paddle right here of this outdoor substation bus. And once again, once it was taken offline, repaired, you can see the damage that was being done. A lot of folks are out there, they're running their lines, they're checking to make sure that they don't have any bad crimps or other connections out there. And once again, this is really applicable whether you've got an outdoor substation or you've got a facility with several different types of indoor substations. A little hard sometimes to scan that indoor equipment, and a lot of other safety practices that go around that. So if anybody would like additional information, or you got some questions about how to do that, be sure to put those in the chat and we can cover those in a bit. But I think most, probably everybody online is familiar with thermographic survey, but I did get a strange question from a client that I thought would have had the right answer to this, but I appreciate that they reached out to me. They said, hey, Mose, can I use thermographic survey to try and head off a lightning arrestor failure? And once again, we can see the failed lightning arrestor here that occurred in their system. And my answer was absolutely. And for the life of me, I couldn't find a picture that I remember taking years ago of an arrestor very similar to this that was failing. But here's an example that I was able to find. We can see this little bit of an additional thermal energy right in this area of that arrestor. And, that is a precursor to failure. So once again, if we have an arrestor that is above ambient temperature, that tells me that it's conducting in some fashion. Any conduction other than when there's a lightning strike is bad. So once again, let's keep in mind to that. And let's see. I just hit really briefly. There's plenty of online thermographic equipment out there these days, whether you use Grace or Exotherm. There are plenty of offerings out there for those most critical situations. If you'd like additional information on that or additional conversation on that, drop it in the chat. I always like to hit on the fact that, it's about the basics, right? When was the last time you opened up some covers on your transformers looking for bad wiring? Walk around. Do not walk past things that are just out of the ordinary, right? A crack in your CT is not normal. And if you begin to normalize it, you're going to lead yourself into danger. So once again, look for things like this and then once again, take action. All right, a couple of my pet peeves. I hate walking around and seeing that there are no control lights, right? If there's no control lights on our breakers, then we, one, don't know the position of them automatically by looking at it. But two, if I don't see a red light burning here, I don't know that breaker has got a good trip coil, right? I don't know that I've got control power to operate that breaker. So it's super important that we keep these lights working. Also important is to make sure that our relays are operating properly. You can see right here in the center of the screen, this self-test warning that I found on a relay one day. It's not good. That means that relay may or may not be in a protective mode for you, right? In a lot of cases, it could be something simple, like something's not programmed properly. But in some cases, it could mean that the relay has completely lost all ability to protect you. And all of our modern relays these days, all of our microprocessor relays do have some form of self-test feature. So make sure that we're looking for those sorts of things when we're out in the field. This is a great example of another control light failure. I actually took this picture in the field the other week, and it really brought back not a great story, but kind of a horrible story that a client had one time. They had an entire 13 kV switchgear line basically burned to the ground. I mean, hundreds of thousands of dollars in damage, maybe millions of dollars in lost production. I don't know, but all because a individual that didn't have the proper experience, wasn't a qualified worker, damaged the 86 relay coil. And you can see that damaged coil right here. Well, once again, nobody knew that he had damaged it, one, and two, they didn't notice that this trip coil light was out. Now, once again, this light doesn't tie to this coil, completely different fines, but this damage would have showed up with no control light. So once again, just like on our breakers, if you're walking around and you don't see a red light, you see nothing, we don't know that 86 can operate. And these are critical systems. This is a critical component to making sure that your substation is going to be safe and reliable. Once again, if it doesn't operate, any number of things can go horribly wrong after that. Simple things like mechanical devices, rust and bugs, once again, looking for those sorts of things, and not just, once again, not walking past a rusty pipe thinking it's nothing. Here's one that came up recently, and I'm sworn to secrecy, at least in public speaking engagements, on who this is. But I do want to point out, because it is a known problem. It's not one that you might catch, not one that I might have caught, right? Just looking at my breakers. But if you have a substation breaker, vacuum breaker in particular, go out there and look at the operator. Here's the operating rod, the drive rod link to close our contacts of our breaker. And what we'll notice is that this over travel arm has missed its bumper. See how it's just off to the right of the bumper there? Here it is in a non-damaged format, right? Well, in this damaged situation, in the situation where it's just off to the right, the breaker will not trip. It is over traveled and the mechanism is not in the right condition to allow the springs to release and open the breaker. That is a very hazardous condition, as you might imagine. So when you're out there doing your walk arounds, let's make sure that we look for things like that. And I say, this one's tricky. It would be easy not to see this. So like I say, if you have any substation class vacuum circuit breakers, maybe get up with me later and I can tell you more about in a non-public format. All right, battery systems. Once again, another crucial item. That's another reason that light might be out on your breaker. but if your battery system isn't working, you're not going to have that critical protection that you need. Most battery systems don't look this bad. We did have a customer here twice recently, two different customers, that by all accounts, their battery system looked fine, and the charger was maintaining what looked like proper voltage, but when they went to operate equipment, the charger wasn't capable of providing enough current, right? So the battery system was damaged, and it was also not able to provide enough current. So instead of a breaker properly charging and being able to be closed, it presented itself as a breaker issue and what turned out to be a control power issue. So once again, check on your battery systems, maintain those as well. All right, let's see, more routine inspections. Are we seeing any evidences of rust in our system? Rust is never good. This is almost always the case. We got partial discharge occurring. And once again, partial discharge left unaddressed can cause not only damage like we're seeing here, but ultimately catastrophic damage, catastrophic failure. Now, once again, you can't see that in most cases. You would need some form of partial discharge device to find that. And you got handheld units like the one pictured here. The other thing is, once again, if you have a supercritical system, I'd love to actually have a client put one of these in so that I could actually see how it all comes together. But the nice thing about a continuous online system, going back to the previous slide, is that it gives us this data trended all the time, right? If we use a handheld device, it's kind of one and done. We're gonna come in, check it this month, or check it next month, or check it once a year. It's a one sample in time, right? We might sample on a day where our PD is really low. We might sample on a day where our PD is really high. But once again, we don't know where we're at without that continuous monitoring, or at least something more frequent than annual. So once again, that's a great way to head off the problems that start off as partial discharge. So anything that's creating some partial discharge and damaging our equipment, PD is a great way to find that. And obviously continuous PD is the best way. So talk a little bit about transformer oil sampling. We're seeing a lot of folks getting into oil sampling, much like going to the doctor and getting your blood tested. That'll tell you a lot about your internal functions. That's what remote sampling ports are all about. So once again, if you are doing oil sampling, if you had pad mounted transformers, please get with some folks. There's several manufacturers out there that make that type of remote sampling port. And once again, takes guys dressed all up, hazardous job, turns it into basically a non-hazardous job. And hate to be I'd say, if I've ever seen anybody trying to sample like this, I'm going to pull them aside and have a conversation, because that's just not safe in any world we live in today. Here's another great idea. What about continuous oil sampling, right? Once again, this is not for everybody. This is for those that have supercritical loads, supercritical transformers, and we want to have as much early warning as possible that I'm having a problem, right? So there are devices out there, once again, several manufacturers. This is just one that I happen to have a picture of, that are going to continuously monitor the oil. So basically it's sampling that oil all the time, running it through an analyzer, and then once again will alarm us on, and once again, this is typically done for things like hydrogen, acetylene, some of your dissolved gases. And from that standpoint, we want to try and once again, it basically gives you the health continuously on our critical transformers. Let's move on into some maintenance testing, and this is where I'll get into some of that new technology. I've been saying for years is that anything electrical and mechanical is subject to failure in any possible time for no apparent reason, and maintenance tries to help us do that. And there's been an IEEE 493 that talks about how equipment left unmaintained will fail, right? And so the longer, and I'll just point this out, the longer we leave equipment, if equipment goes more than 24 months, we tend to have more problems with it. Probably no surprise there. Turning our attention to 70B, right? There's a point where the cost of maintenance and the cost of damage are at the minimum point. You can spend a ton of money on electrical maintenance, and once again, you can spend very little money on electrical maintenance or go a long time in between, but ultimately that's going to lead to unplanned failures. So let's talk about transformers really quick. What do we recommend? Generally speaking, transformers should be maintained every 1 to 5 years. We're going to do things like insulation resistance, turns ratio test to check the, once again, check the ratio of the transformer. Winding resistance test. This is a great test to check internal connections and components, including our load tap changers. Power factor testing, I'll talk a little bit more about that. Sweep frequency response. This is not a test that needs to be done all the time, but it can have some super valuable information, and I'll show you that. And then a test, once again, kind of that new test category. Here is one about dielectric frequency response. So moving through those, power factor testing. Here's a great example of a bushing that we tested just the other week. And I'm so glad we had this information because we tested for a variety of frequencies. And we can see, we got let's see, was it H1 and H3 way down here at, 0.25 or thereabouts, nice and flat and perfectly together. We'll notice that H2 has this little curve going on. Now, once again, it's bad at 60 Hertz. It's at 1.2 at 60 Hertz. So it's already bad, but we can see just a little bit more information about it in this response that we're getting. So once again, transformer testing, and in particular, bushings are one of your higher components of failure in a substation. So something to keep in mind. The other thing, by doing a full transformer test, by not, I'll just do a little bit. By doing a little bit more, by doing the bushing test, you'll also find hidden problems, right? This was not a problem we expected to find. And what you'll see is this is what's called, for those that maybe know transformers, this is the capacitive tap test point. This is how we test a bushing. We remove this cap, and then there's a connection point in here where we can test and get information about our bushing, like I just showed you. Well, sometimes these caps don't get put together don't get put together properly, and they can begin to arc and deteriorate and cause damage. You can see the erosion in this cap right here. You can see the corrosive dust that was created over. By all estimates, this transformer hadn't been touched in 10 to 15 years. So once again, this problem has been hiding there, waiting for a moment to fail. And fortunately, the client started doing a testing program, and now we can head this off. Where before they might have seen that bushing fail down the road and never known why. So just some more notes about power factor testing. We can get the same kind of information about moisture in our transformer by, once again, testing over a variety of frequencies. And moisture in transformers, you could have a perfectly tight transformer, and just the natural aging of the paper materials that the transformer is made of will generate and create moisture in our oil. Now, once again, I'm going to point out moisture in oil tends to be the small amount. The moisture tends to hide in the cellulose, in the paper of the transformer. And this picture does a great job of just kind of, showing the proportions. So if you got an oil, at 16 parts per million in oil, you might have 200 kilograms. I mean, just a lot inside the paper. So once again, keeping a track of our moisture by doing some oil testing, which I mentioned earlier on. And like I say, I mentioned earlier about, keeping our transformers cool. Well, we'll also point out that if we keep them dry, we can expect to have a longer life. So a transformer that's operating at 4% moisture at 70 degrees C has about a 10-year life expectancy, right? A transformer that is operating at 1% moisture at 70 degrees C, we can expect to have about a 100-year life expectancy. So once again, keeping our transformers cool and dry is of the utmost importance. And once again, that's a critical asset, right? Lead times on big transformers these days are pushing up over a year. And once again, they're not inexpensive to replace. So keep that in mind. If you do have, or if you are concerned about moisture in your transformer, we can also take that testing up another level using the dielectric frequency response. And that test basically does a power factor from 0 Hertz all the way up to 1,000 Hertz. And once again, looking at how that transformer responds. And once again, a new transformer is going to be the curve similar to this. An aging transformer is going to push up and to the right. And once again, this is some of that new technology. SFRA. Another relatively new thing, or at least something we don't see people testing, using as far as testing goes all the time. And, this is a general response curve. We got core influence, interaction between winding and structures, and earthing influence. And once again, this is basically just a general picture. So let's talk about what that might look in the real world and where we might see some differences. And so here's some recent testing that we did. And we'll note here that we have X1 and X3, and you'll notice how perfectly aligned these two curves are, right? From start to finish, they're in great alignment. But when I compare X1 to X2, you'll notice in that the core influence area, as well as the winding to winding area, you can see that there's a shift between these items. So once again, this is a transformer that's never had an SFRA conducted on it before. So could this transformer have always been built this way? We don't know, but we do now have some baseline information that we can utilize for, so that we can continue to monitor this, right? And we also have a sister unit that we're going to be testing soon. It'll be interesting to compare the results between two units made at the same time. Breakers. All right, so once again, whether we got medium voltage breakers, low voltage breakers, SF6 breakers, vacuum breakers, they all have a lot of the basic same characteristics, and particularly a lot of the same testing that could be applied to them. Once again, we're looking at 1 to 5 years taking our breakers out of service. And so once again, we're going to do insulation resistance, checking those components that keep our breaker from going to ground. We're going to check contact resistance of the current path and the contacts. Are those items in good repair and making good connections? Timing. I'm going to talk about first trip timing, which I think is a test that is underutilized. We're also going to talk about, we can also power factor our breakers, do vacuum bottle integrity tests for our vacuum breakers, but there's a better test maybe called the magnetronic atmospheric condition test, or short the MAC test, because that's a mouthful. And then finally, SF6 breakers. I got some ideas on SF6 breakers for our audience today as well. And that's where I'm going to start. Let's talk about SF6 breakers. Now, they come in a couple of different varieties. These are some substation types. This is a 161 class breaker over here, 35 kV breakers here. We're seeing gas insulated switch gear coming in there. We've got circuit switchers that are filled with SF6 gas. And as you're doing your routine inspections, please make sure that you check your gauges, that you're not leaking gas. I've gotten more than one phone call from folks that say, hey, I don't have any gas in my breaker. And of course, that's never a good thing. So how do we address that, right? But here's an interesting test, and I say interesting because once again, I don't see a lot of folks doing this. This is a company that we like to use, and Randy, we really ought to get the TJ H2B guys on here sometime. But once again, we can pull a gas sample. Recently, we've seen some 10-year manufacturer specifications where at one time the manufacturer would encourage you to take the gas out of the breaker, take the breaker apart, inspect internal components, and then go through the process of putting it back together. And we've seen some manufacturers recently, particularly southern states on their circuit switchers, has basically removed that requirement. They don't really want anybody cracking their breakers open in the field to do internal inspections. Well, one, I think that speaks to the fact they got plenty of evidence that they're not seeing a lot of degradation on the internals. But two, we're losing out on some valuable information by not doing that inspection. So how can we get that same information by being less intrusive? And one way to do it is by taking an SF6 gas sample, not just for moisture or SF6 density, but to get into the decomposition products, because there are some really smart chemists out there that can tell you that if you've got sulfur hexafluoride environment and you create an arc with various components that make up our breakers, like tungsten and Teflon and other and stuff that I probably couldn't even pronounce, you'll get byproducts, right? And these byproducts can be an indication of problems. And here's a great example that I took from a paper by the company, and that is they had a breaker that was they were concerned about. So they did some of this testing that I'm talking about, where they took the sample using this bottle kit, sent it to the lab, and it came back with carbon tetrafluoride. once again, a decomposition product of the Teflon material that made up part of the breaker. And once again, after getting these results, they decided they would take that breaker out of service, take it to the factory, tear it down, and sure enough, significant damage was noted on pole 2 that was not noted on pole 1 and 3. So once again, this is a great thing. Just like a transformer oil test report, SF6 breaker test report is fantastic. Vacuum breakers. Once again, whether they're a substation type, metal clad, there's a lot of great testing that we've already talked about, insulation resistance, contact resistance. But how do we know what the condition of the vacuum bottle truly is? And historically, we've done that with an AC over potential test, right? We apply a voltage. If the open breaker does not break down on the voltage test, then we deem it good. But the one thing that we never knew or we couldn't tell is, hey, am I sitting at this point on what's called Paschen's curve, right? This is the curve that is the dielectric strength of dry air, right? So if I've got a really good vacuum way over here at -5, -4, -5, you can see we've got a tremendous amount, 400, almost 400 kilovolts per centimeter of dielectric strength. But you'll also notice that if I'm sitting right here at -2, that I'm very close to going over the edge. And once I go over this edge, I go from a really high dielectric strength very rapidly to a very low dielectric strength. So our traditional test was never able to tell us where am I at. It was always a go, no go test. And you can see that I'm a go. I mean, I'm going to pass this test. I'm going to pass this test all the way until I'm basically, going towards atmospheric pressure. So we want to keep that in mind. And once again, we've got a test called a magnetronic atmospheric condition test, or the MAC test. It not only applies a voltage, but a magnetic field around the breaker where we can measure that ion gap and then estimate the pressure that's in the bottle. So once again, we can begin to tell you where you're at on this curve so that you can take action. First trip testing. Now, this is a test that I think is woefully underutilized. I think this is a great test. I'm going to have you guys do a little mental exercise with me really quick. I want you to picture that I'm going to ask you to get into a squat and then explode up in a big jump, right? We can all picture ourselves doing that. We're going to go to the bottom. We're going to jump up. It's going to work out great. Now, I want you to picture you're going to sit in that squat for 10 minutes. And then think about how much energy you're going to be able to explode upward with, right? It's an interesting experiment because if you're being honest, it's probably going to be like, oh, it's going to be a little bit harder to get out of the bottom after I've been sitting there for a while. And that's what we ask our breakers to do, right? We ask them to go closed and stay closed until we need them to open, right? That might be being closed for a year, 3 years, 5 years. Once again, I think I've interacted with breakers that haven't been open since the day they were put in service, right? So once again, how do we know our breaker is going to operate well? Well, I mentioned that we could do timing tests, but when we do the timing test, we're actually taking that breaker out of service, and so we've actually operated it, right? We've moved the mechanism, we've kind of rolled all the bearings and everything like that. So when we go to do our timing test, are we getting a real image of how that breaker is going to perform after I've let it sit there for a while? And once again, we can do this both with test equipment, or we can take advantage of relays that we already have in our system. And once again, even using a fault event gives me a picture of how our breaker is going to perform in that first trip environment. And to note that, right, here's the initiation of the trip signal right here, this red dotted line. That's the initiation of the trip signal. That's when the relay finally timed out and says trip the breaker. And then we can see this purple line, how long it took the breaker to trip from command to trip to actually opening and indeed energizing the system. And then it's just a matter of counting the cycles, right? So if I pick this green waveform here, there's 1, 2, 3, 4. So before the 5th cycle of the green phase, we are at a de-energized state. So once again, that gives me a great picture of this breaker is going to operate in 5 cycles like most systems are designed to do. Well, what about my folks with low voltage breakers, right? What about you guys that have those low voltage substations? What about you? Timing first trip testing of a low voltage breaker is a little bit more complicated. There are a product out there that we're working on that can do first trip testing of breakers using vibration. But there's also manufacturers like the AC Pro 2 here, made by Utility Relay Company, that has a sluggish breaker feature. And that sluggish breaker feature allows you to know, hey, in the event of a fault, did my breaker trip as fast as I was expecting it to? And once again, it is important. I'll point out to everybody that when you modernize your breaker to a AC Pro 2 and you set up this sluggish breaker trip, when you're doing your trip testing on the high current test set, which you should do, of course, right? Anytime you've modernized a breaker, document what the average is of your trip times, right? How long does that breaker take to trip? Because it could be that it takes a little bit more than 33 seconds, which is the default setting. And so you might need to adjust that up a little bit to make sure that that breaker is going to be monitored properly. And Randy, I'm noticing that we got about 8 minutes left at the top of the hour. How about I pause and are there any good questions that we could address?
No, I mean, I think it's great information. And you just got a few slides to go. You should finish and then we'll go to the questions.
Okay. All right. Well, I'll keep on rolling. I'm a big fan of taking advantage of technology, right? These are two great items of technology. Here's another great opportunity to take advantage of technology. You know, we can see that we got a line of, oh, sorry, turn off my pointer, of electromechanical relays. That's what these gray black boxes are down here. This is what it looked like when we finished, right? Just a nice clean look. But, you know, but what are some of the advantages of that, right? Why do I want to go through all the time and the trouble and the money to upgrade my relays? Well, a couple of different reasons, really. And one I want to point out, of course, is one of my pet peeves. You're walking around and there's a target on the relay. Well, in the old days, that was all we do is, yep, we had a trip, right? That's what that little orange window is telling me. I had a trip. Doesn't tell me anything about the trip, right? Well, when we upgrade our relays, we get all of this tremendous information, right? We can see here's the fault that occurred. We can, you know, once again, we get our information about how long it took our breaker to trip, things of that nature. So it's really important to do that. And really quick, you know, once again, back in the day, we got an orange target and you get a phone call and says, hey, I was sitting at the house on a Saturday, getting ready to maybe crack open the first cold beer after mowing the lawn, and get a call from a client that says, hey, I had a breaker operation and I wondered if it was safe to turn it back on. I said, well, what kind of trip was it? A time or instantaneous trip? And they said instantaneous. And I said, no, you don't want to turn that back on. Hey, honey, hold my, you know, I'm going to go to the customer site. And, you know, once again, they were ready to turn us back on. Now, they did have oscillographic record technology. And I opened that up and I saw a fault that looked very much like this. I'm like, guys, you had a 10,000 amp event. There's something wrong out in your system somewhere. And they're like, no, we rolled the system. We didn't find anything. And I said, well, let's go ride it again. And as I'm riding around with them, we're not finding anything. And I'm like, well, what's around the corner over here? And they're like, oh, you know what? We do have one more transformer over there. And of course, always the last place you look, right? That's where we found the problem. Matter of fact, the switch door was actually buckled out. So once again, getting that information and having those oscillographic records is super important. And I guess to wrap up, I mean, I want to see you guys using qualified workers. I've covered a lot of ground. I hope you took tons of notes. I hope you have tons of questions. But qualified workers, right? This is a great little image of somebody that really wasn't qualified to install a system of CTs on this medium voltage gear. They didn't understand the concepts of how a medium voltage power system works and how current transformers should be applied. So keep that in mind. I want you guys working with qualified workers and taking advantage of the fact that there's opportunities for you guys to do both routine maintenance and routine inspections and routine maintenance testing. And once again, let's make sure we're working with qualified folks. And if you're unsure at all, I'm always happy to answer any questions. And like I always tell people, I'm available 24 hours a day, 7 days a week, 365 days a year to answer your questions. And Randy and I were chuckling about this. I thought I'd share, you mentioned 25 plus years in the industry. So from the young guy that crawled through manholes to the old guy that still goes out and tests transformers, I hope you get something out of this. And I hope we have some great questions.
You do. Thanks very much, Mose. Good presentation. Good overview of all the testing required on this equipment. What is your suggestion on transformer bushing monitoring? Which system is most reliable?
That is a topic that I'm actually going to be researching for my next presentation because, and matter of fact, there's actually somebody putting one on here soon. I've only installed one system. It was ages ago to monitor bushings continuously. And once again, we're just looking at kind of that continuous power factor of a bushing. I don't have a particular brand in mind. And unfortunately, we don't really, I say unfortunately, we don't see a ton of online bushing monitoring systems, but given the opportunity and given the dollars, I highly recommend installing continuous monitoring on anything.
Okay, next question. Can you talk more about failures on RV leads?
RV leads.
SS, maybe you can specify what you mean by RV. Can you talk? Can you? Sorry, go ahead.
Thank you, Randy, and thank you, Mose. Actually, this is about the internally transformer winding. After all the three windings are done, and then the joints are taken out to the bushing, right? Just bushing what we see outside. The below that connects the conductor connects to the main lead, right? So that joint is called the RV leads.
Okay.
Okay, well, are you familiar with that, Mose?
I think that I'm not prepared on that one.
Right.
It sounds like we're talking about the connection between a draw lead and the transformer itself.
Can you talk something about different types of SS arrangement? 1.5, when to use H type and A type of frame?
Oh. I might have to pass on that one.
Yeah. SS, why don't you write these questions to Mose later? They seem very detailed. Okay, SF6 gas tests.
Yes,
when
sir.
this test is done, is the gas being tested purged into the environment?
That is, so there are some test sets that basically take a sample and it does purge it to the atmosphere. That is one of the advantages of the bottle, and let's see how quickly Mose can maybe find that for us, is that it does not purge it to the environment, right? We have one cylinder that is used to, and this comes in completely evacuated. One bottle is used to take a waste sample, so basically get the air, the air in the line purged. And then the second bottle is used for the actual quality sample. And then we close off the system, and basically you have it's almost, I say it's the size of a human hair, but it's a very thin little tube. So when we break those connections loose from the gear, I mean, we are losing the minimal amount of gas possible, as opposed to some of your standard test sets that only test moisture and quality.
Okay, Steve Evans says Mose SF6 gas testing proves to be very effective for detecting hidden issues, but as we move towards a more sustainable future, do similar tests currently exist for SF6 alternatives? I imagine the chemistry is different as there are different mixtures out there. Can you speak on your experience with this?
Yeah. Great question. This was actually a part of a presentation that I saw by TJ H2B, is that they are already in the process. And once again, a lot of people on the webinar may not know that there are some alternatives to SF6 that are being developed and marketed by a variety of manufacturers. And that TJ H2B is already in the process of collecting data to, once again, begin to build the chemistry of what do failures look like. So the short answer is yes, they're working on that.
Okay. Do you have a service provider in the Washington State Puget Sound area?
Yes, I
Okay.
recommend CBS Field Services.
Good. What tests do you recommend for an electronic protection relay like a Multilin 860, and what frequency?
Oh boy, we're going to get ourselves into a heated discussion about what we need to do as far as relay testing goes these days. Manufacturer says we really don't need to do much, right? And that you can go 3 to 5 years without really doing much in the way of relay testing. Of course, never ask a barber if you need a haircut, because the answer is always yes. So if you ask me, I'd still love to see you test your microprocessor relays at least every 3 years. Once again, routine inspection of the self test, but offline testing, I do like to see at least every 3 years. And the things we're going to look for, and once again, they're kind of some of the basics. Does it meter properly? Are our inputs working? Are the outputs working? And then I usually like to check a little bit of the logic. I should try and find a way to do a whole presentation on, I've got no confidence in my logic, therefore I'm not going to try it. Well, that's a horrible place to be, because then you don't have any confidence in your system and how it's supposed to operate. And operating from a state of ignorance is a recipe for disaster.
Okay, and that was the last of our questions. So thank you very much for the presentation. You did a great job. Thank you once again.